What a racket! Of all the sounds around us, there are some we want to hear and others we definitely don't.
The train now at platform 2 is for Finsbury Park and Battersea Park.
Whether it's music or noise, all sounds have something in common. What is it? And what is sound? Here's a soap film. Watch what happens when it's placed near to someone playing the violin. So how does the music produce the patterns on the soap film? We can't see sound, but we can see its effect. Using a stroboscope makes it easier to see the vibrations of the string. The kinetic energy of the string is transferred to the air, causing it to vibrate. The air transfers its kinetic energy to the delicate soap film and it vibrates, producing these patterns. Any note makes the bubble vibrate at a certain speed or frequency. With the help of the strobe, we can see what happens to the string when the violinist shortens it to make a higher note. What happens to the bubble? The air vibrating around this tuning fork. But with high-speed photography, we can see the tuning fork itself vibrating. Here's a tuning fork which makes a higher pitched sound. Can you see what difference that makes to the vibrations? We still can't see the air vibrating, but look what happens when we attach a light spring to the tuning fork. The vibration of the tuning fork sends waves along the spring. The waves are made up of some places where the coils are closer together and others where they're further apart. Let's slow the film down for a better look. For any note, the distance between the start of one compression and the start of the next is always the same. This is called the wavelength. Now look at the coils as we speed up the film. The wave travels from one end of the spring to the other, but the coils only vibrate backwards and forwards a small distance. They don't move with the wave. When sound travels through air, it is the molecules that vibrate in a similar way to the coils of the spring. They don't move very far either. So when you sit at home, even if you turn up your music very loud, it's very unlikely that it will be blown over in a rush of air molecules. We've seen that sound travels as waves, but how fast is the energy transmitted? Imagine you're at the track and take a look at the start of this race. Does anything strike you as strange about that? Are you sure? Doesn't sound travel slower than light? How much energy can be transferred as sound waves? This lorry is about to be blown up by a particular type of sound wave. An explosion at the end of the tunnel sends out a shock wave, a single compression and expansion of air that travels at the same speed as sound. Shock waves can be very destructive, as we've just seen, but they can also be very useful on a smaller scale. This patient has a kidney stone, a ball of calcium salts which is blocking the exit from his kidney. It's very painful. The doctors aren't going to blow him up, but they are going to use shock waves to smash the stone. Shock waves are produced in the bath by an electrode, a bit like the spark plug on a car. They are focused through the person's body and onto the stone. Six or 800 pulses later, and the stone is smashed to gravel, which passes out in the urine, and the patient has nothing more than a bruise. At the volume we're used to hearing it, sound doesn't normally destroy anything, but music does sound different according to where it's played. Can you see what properties of these two rooms make the violin sound different? Even if the echoes aren't a problem, in a big space it's often difficult for a musician to make themselves heard. However much energy you put into playing, sometimes you just can't play loud enough. What could you do to solve this problem? This electric violin has a microphone attached to the bridge. We can also use a microphone on a normal violin. Microphones and loudspeakers allow us to hear music at greater distances. How do they do it? Remember the bubbles? Microphones work on the same principle. The energy of the sound wave is transferred to another type of delicate membrane made from plastic. A coil attached to this membrane vibrates with it, producing electrical signals as it moves up and down through a magnetic field. The strength of the electrical signal is increased by an amplifier. And the loudspeaker works like a microphone in reverse. The electrical signals in the magnet cause the coil attached to the paper membrane to vibrate. The signals are bigger, and as we can see with the stroboscope, the movement is bigger, causing a larger volume of air to vibrate. So, the sound is louder. Our ears also have an amplifier, but not with wires and magnets. Let's go in and take a look at how it works. This part of the ear has two membranes, like the skins of a drum, linked by 3 small bones. The sound from outside hits the larger outer eardrum and is transmitted by the bones. Can you see why the vibrations of the inner membrane are larger? Now we've got the ear sorted out, listen to this for a second. Lots of modern music combines traditional acoustic instruments with electronic instruments and other sounds. So is there a difference between the sound waves produced by musical instruments and other noises? Any instrument produces a distinctive pattern. This waveform monitor shows the pattern of sound waves we're hearing. That's what the sound of a saxophone looks like. And this is a violin playing the same note. Notice that for musical instruments, the pattern is very regular. Now here's a cymbal, much more like a noise. What's the difference in the pattern? Musical instruments produce quite simple patterns of sound waves. Noises are more complicated, containing many different sound waves. What an irritating sound. Definitely a noise in my book. But hang on a minute. Now it sounds like music. Well, almost. How did that happen? This machine is called a sampler. Musicians use it to record any sound or noise and then play it back at any pitch they like. My mum always said that modern music was just a load of old noise. Maybe there isn't such a difference. What do you think?